Welcome to our class. We continue with our series of deploying our contracts, and this time we are deploying to scroll Sepolia. And remember, you can use the same process if you wanted to deploy to scroll mainnet. Just a few changes here and there on the URL. You want to change the URL and the chain ID and a few things, but the rest, the process of deploying will be the same. So the difference will just be maybe in the setting of the environment, but the rest remains the same. So this process, you can always apply it in from Sepolia testnet to mainnet. Of course, mainnet is always our final target. So today's class, we'll be looking at from the scratch, how do we write Noir circuit? How do we generate a proof? How do we generate a solidity verifier, that is the contract? Then from there, set the environment for deployment and deploy to Sepolia, scroll Sepolia. So that is what we intend to do. And after deployment, we will want to interact with the deployed contract. So the objectives, today's objectives: one, understand and construct a privacy-preserving Noir circuit. Two, prove, and that is now about the circuit that we'll be writing. We want to prove a zero-knowledge proof of two secret values whose product is 42, but these two values will be private. We are not exposing the private. What we expose, no, the product. What we're exposing is the sum of those two numbers. So for the product is just a condition that the two numbers must meet. That we want two numbers whose product is 42. But then what we reveal to the verifier is the sum of these two numbers. So the verifier will want to check whether it's true that those two numbers, the sum is correct. Now, so after writing this circuit, we'll generate a witness and proof, zero-knowledge proof, using NAGO and Barentenberg. And then after that, we set up scroll Sepolia and deploy a ZK verifier contract to scroll Sepolia. And then we want to interact with the verifier on-chain and off-chain using Foundry. Now, just to explain about setting up scroll Sepolia, for me, I use MetaMask. My account is on MetaMask, and scroll Sepolia is not a network there. So I'll be taking you through the process of adding scroll Sepolia as a network on MetaMask, for those of you that don't have it. And then after that, I show you how then do you get free ETH into your account, because we'll be using free ETH in our deployment of the contract. So we're not going to use real ETH. And then after that, we set up the environment for deployment, and that means we come up with a file we call .env inside the contract folder, and paste in a few keys. For instance, we'll paste in our private key, which we're getting from account. And then apart from this private key, we're going to paste in our URL, that is UPC URL, and the other things as I'll get it to mention to you. But before going to the depth of what you're going to do, we first of all recall what zero knowledge is. So part one, looking at zero knowledge with the Noir. And what is Noir? Noir is a domain-specific language. Good. So first of all, we know what is zero knowledge is. So I'm just telling you what is Noah. Of course, we know it. We said Noah is a domain-specific language that is used for writing zero knowledge circuits. So we'll be using Noah to build this circuit. And zero knowledge proof, we know what it is. So we mean we have the verifier and we have the prover. The prover needs to convince the verifier that he knows two numbers, X and Y, such that their product is 42. Then it is not going to reveal these two numbers to the verifier. It remains a secret. But the only thing that the verifier and the prover would get to know is the sum of the two numbers. So he reveals to the sum, he reveals the sum, the prover reveals the sum to the verifier. So this circuit then demonstrates minimal disclosure and ZK arithmetic constraints. Now, circuit description, just before we look at the circuit itself, we have X, which is a field, Y a field. Then in the public output will be the sum of X and Y, which is then is known by both the prover and the verifier. Remember, it's the prover is the only one that knows what X and Y are. So these are the constraints. X dot Y is 42 and the sum is X plus Y. So our Noah circuit will look something like this. So if you open your WSL and your VS Code or whatever format that you use in writing your circuits, you paste this into main.nr. Now, so looking at this circuit, you discover that X, this field X is private, the field Y is private, but then the public field is what comes out is what is public. What comes out is the sum. The sum is what comes out. But this is just a condition that X and Y must meet. X and Y must be that their product is 42. And you can always generalize this circuit so that you can just even change 42 to any other number. That's what I mean by generalizing. Now, when you're writing this circuit, you can also add tests just to be sure that your main function is behaving as expected. You can add tests, and that is what I've added here. Previously, I taught you how to write tests in Noah. It's the same style we are using. that you have hash, then test in bracket, then your test is here, functions, you're testing a function. So supposing you have 6 and 7 as the two numbers. Now we know that it's true, therefore, that their product will be 42. But what you then give to what we expose is 13. That is what the verifier gets to see, the sum. So so that the verifier is not able to know what numbers you took. Now, if a test is supposed to fail, then you write test. In brackets, you write should fail. Should fail. That is so that when you run it, it will not fail. Now, this one, without the word should fail, then it will panic and fail, because when you look at these two values, their product is not 42. So it's bound to fail. Now, after you've written that circuit, you can do Nago compile. Nago compile. And then you can also do Nago test. Always good to add this unit test just to be sure that your circuit behaves well for every. So you see, when you're testing all conditions, and all you test, for instance, even the boundary values, to see whether your circuit behaves okay with the boundary values. This Nago test, Nago compile, you'll be doing it on your terminal inside circuit. Inside circuit, let me just remind you, you had your WSL. You had your WSL. Now, so inside you on your terminal, you opened where you usually store your documents or your files or projects. For me, I normally store in Rust programs. So after this opens in your terminal, you just say cd Rust programs. That is where you store your projects. And once it opens, you want to create a new project, and you want to call it a project. So you just do directory project, make, this is MK directory project. Now, so then you cd project to get inside, you cd it. Then after getting inside project, you would make another directory, and this time call it circuits. Okay, so after that, you get inside circuits, and then just do Nago init. So this then creates a project, a new project, and you define it will just inform you that a new project has been created. Now after that, get outside circuits, cd dot dot, that gets you outside circuits, that you now get into project. It's this project that I want to open. So you do code space dot. Once you get, I said you're inside circuit. So you just say did cd dot dot enter, and then it gets you here. So while here you do code, then some space dot enter. That one opens for you VS Code, where you now go and paste the above main.nr. You'll find some main.nr that comes by default. Replace it by the one I've just shared above, and then you can now do nago compile and do nago tests, because you can also paste there your tests, unit tests, and so on. Okay. Now, if you want to generate a proof like this, you would create project. You create a folder called JS. Let me just share my code. This is a complete one because we had done this before. So what I said was this circuit. You came inside and replaced your default main.nr, and you replace it by what we said will be our circuit. And so this is our circuit. And then you will also add some tests. You can see I've added tests here. Only added 3 tests. And if a test is to fail, then you add should fail. And for instance, I can see this one is supposed to fail because the product here, of course, is not 42. This product is not 42, and that's what I've written as the reason. Although the sum is 13, but the product here is not met. This condition is not met. Condition that the two values x and y their product should be 42 is not met. So that one is going to fail. And even this one, although 6 and 7, their product is 42, but their sum is not 10. So again, this is supposed to fail. So I write here should fail. So that when you run, you just go back to, see, I'm already in contract. So I get in outside and get inside circuits. Get inside circuits. While you're there, you can say nago compile. It compiles without errors. You can also say nago test just to see if your unit tests are correct. You can see it tells me that there were 5 tests and they are all passed. All the 5 have passed. Good. But that is not the point. The point I wanted to show you is that you also want to generate proofs. And to generate proofs, I said you must have this folder called JS. And this JS should have what it has in my folder here. You can always clone my repo. You can always clone my repo. I shared this repo in my, in fact, yeah, if you go to my, just go to my GitHub and you can see the repo. What's the name of this repo? Let me just go back there. Just see which repo I'm going to, you can see this. Scroll Sepolia Noir. Scroll Sepolia. So you can clone this. You can clone this. What is you can share the link. That makes it easier. I can share the link. That makes it easier for you to get it. Where do I share it? Let me just go back. Yeah, I can share it here. This bottom here. This is the link. So just say git clone, then you end here by .git. So when you run this, you get to clone it. You get to clone it when you run that. Good. Now, you need therefore to have this folder JS. Very important to the JS is this generate proof.ts. Generate proof.ts is very important there. Just a minute. Okay, so what I was sharing here was you have this generate proof.ts is very important and is here. Something we've looked at before. Do we know how to write it? The other thing that is important here is package.json, then ts config. Then of course yarn lock would also come in handy. So you need to have these things. Then you will just say yarn generate proof. The proof will be generated, and once it is generated, it is stored inside the circuits target. So you can see here we have proof. This is binary, you cannot read it. You can also have public inputs generated, but you can see them here. At this point, it was binary and so on. So you have all those being generated and stored inside the circuit. And the command for generating the proof is what I had shown here in our notes. You must have run nago execute before you run this command, because nago execute gives you the witness that is then required to generate this proof. It gives you the witness. Then once you have the witness, you run this command to get the proof, this command here. Now, with this command, you have the proof, but you also require the contract that will be deploying. And earlier on, I had shown you how to generate it. And we had a script called build.sh. Inside this build.sh, you have the command for generating that. Of course, this command, you can even run it directly without having it inside the script. It's just bb write solidity verifier and so on. So it's using whatever the proof verification key, whatever verification key that is inside target. Now this, I'd skipped this part where you're writing the verification key. So first of all, you must have the verification key inside your target. Then once you have the verification key, then you would use this command now to generate our contract that we require to use for deployment. Now, once you get, once you have the solidity verifier, you are now ready to deploy it. But before deploying it, you need to ensure that the environment is set for deployment. And apart from that, you must have your scroll Sepolia on your MetaMask. So part 2 of this lecture is scroll ZK EVM deployment. So just before that, I'm telling you that scroll is a ZK VM layer 2 build on Ethereum. It's fully compatible with the Solidity Foundry had that and MetaMask, and is ideal for on-chain verification of ZK proof. So it's important you know that so that you can use it. Now, once you know that, now the next thing is how do you add scroll Sepolia to MetaMask, because it's not there by default. It's not there by default. So you would go to MetaMask and then add a network. Then when you click on add network, you enter these details. So let me just get you there so that you can see what I'm talking about. So first of all, where I want us to go is the browser. I want us to go to the browser. So I want to stop sharing this and take you to the browser. So this is our browser. And while here, our MetaMask is here. It's an extension. Click on it. When you click on it, this is what you get. It opens. So this is already the account I want. But I want to add MetaMask. For me, I already added MetaMask. But what you will do for you to add, if you will not, no, I already added Scroll Sepolia, and that's what you want to add, Scroll Sepolia, not MetaMask, but Scroll Sepolia. So you will come to this here, where we have, yeah, this is where we have networks. You can see I've already chosen Scroll Sepolia, but for it will not be there. So when you come to Popular, check for Scroll Sepolia, it will not be there. If you come to Custom again, it will not be there. For me, I've already added it. So how did I add? I came to this custom and came down here where they say add custom network. And I fill this. These are the details I was asking you to fill. So you have network name, the default, RPC URL, chain ID, a current symbol, local explorer, URL, and so on. So those are the details that you need to have. So you just fill them inside that and then save. Here they are, here they are. So these are the details you would get to fill in. So now after that, you'll be having a scroll Sepolia on your MetaMask. The next thing is you need free ETH to do the deployment on this testnet. You're not going to use your real ETH. So for you to fund your scroll Sepolia with the test ETH, there are various ways, but the easiest of them all and very recommended is using Telegram. Go to Telegram and just search for at scroll Sepolia up, no, at scroll up underscore Sepolia underscore bot. And then join the faucet group. While inside, well, in fact, while inside you want to just type this while inside. And once you type this, they send 0.05 ETH directly to your account. Now, this is what you're typing here is, this is your address. The address you got from, this one you get from your MetaMask account. So you write this slash drop some space, then your account. So where are you getting this account from? Somebody might be asking, where do you get this account from? Let me again take you back to MetaMask, but I show you the account. And always make sure that this account has no ETH, real ETH, has no real ETH, so that you're not exposed to fraudsters. Now, this is the account I want to use. So when I click here, I want to use Scroll Sepolia and the account is here. I just copy this, Scroll Sepolia, you can see address copied. So this is the address of the account that I'm going to use. Now, after we've done several things here, other than writing the circuit, generating the proof and the verifier, solidity verifier, we've gone forth to add the scroll Sepolia to MetaMask. We are done with that. We've funded our scroll Sepolia account with the free ETH. The next step is to set up the environment for deployment. So to set up the environment for deployment means you'll add a file in your contract folder. Let me take you back there. This is my contract folder here. Contracts. So the file I'm talking about is this .env. Inside this .env, this environment, you have to add in private key that is coming from your MetaMask account. You should add scroll Sepolia RPC URL. This one you can get it using, you can go back to a lesson I taught previously. I've taught several lessons on deployment. I deployed to Base Sepolia. I deployed to Ethereum Sepolia, and so on. You can get how to get this. I even taught how to, the initial class on deploying on scroll Sepolia. This is the second class I'm teaching. Now, this is the ID, and this is the Etherscan API key. This is only used for verification of the deployed contract. And then you must ensure that this thing goes to, this file goes to gitignore, that it's not committed to a GitHub. If you want to commit your project to GitHub, this part just ensures that your file.env does not get to a GitHub, just to secure this vital information, especially the private key. Now, how do we get that private key? And again, I'm taking it back to MetaMask. Taking it back to MetaMask here. Okay, want the private key. So while here, while you click on these three horizontal lines, then account details, then private keys, and then it asks you for the password. You just enter your password and then confirm. Now it gives you private key for all your accounts, but our interest is just on scroll Sepolia. And you would just copy it. Of course, it will be the same. This private key, since it's the same account, doesn't matter the network you're in, you're using, the private key will be the same. That is why we are saying it should be, private key should be kept anonymous. It should be kept secretly, that is. It should not be exposed to the public, be kept private. Because supposing you had real ETH in Ethereum mainnet or Base mainnet or Scroll mainnet, and you have exposed the private key, although you got it from Scroll Sepolia, it's the same private key for your account. The account is the same. What is varying is just the network. So when you expose account, it's exposed for all networks. Now, after setting up the environment for deployment, the next thing that you need to do is to ensure that your Foundry has these optimizer settings, just to ensure that whatever comes out as a contract is deployable, because Noir generates contracts that are bigger than what can be deployed. So you then have to use optimizer settings just to navigate that. We are now ready to deploy. You can do it manually or you can do it using a script. I began by using a script. So you can write this script inside your contract scripts. Inside your contract scripts, I again show you. This is our contract. When I click on it, there is some script here. Inside that, I create a file called deploy.s.sol, and I just paste this content here. Now this one is for later. This interact.s.sol is for later when we want to interact with our deployed contract. You can also interacting with it can be done manually off chain, or you can do it on chain. So again, when I come to that, we'll be looking at how that happens. Our interest now is just to deploy, and this is what the script is. This is the script that I was showing you in our PDF. Now, after that, you can just run this command, and this command deploys. You're running this command inside your contract. On terminal, you get inside contract and run this command, deploys. Now you can follow it on chain and see what has been deployed. Now these notes, if you follow the notes on my what I've given on my GitHub, there are more details. Okay, so right at my GitHub, here is the repo we talked about. Just want to look what it's README. It's going through all these steps. You can see it's telling you about setting the environment, manual deployment. Before you do manual deployment, you must run source.env, and then you can deploy by this command inside your terminal contract. Now, if you get an error of limit size, we had already talked about adding this to your foundry, just the optimizer settings, because that limit size means error means that your contract is beyond the size that can be deployed. So you can bring it to correct size by this, adding this to your foundry. So that your foundry looks something like this. I just added this one also for the sake of deployment, and this for the sake of verification. You can add them there. Now that is if you want to deploy manually, because you can deploy manually without a script. You can deploy manually without a script. You just run this command and it deploys manually. But if you wanted the script, that this is what we were discussing in our PDF. You had to add this inside script, and then inside deploy.s.sol, add this code I'd already shown. Yes, and then you run this. Now you just run this command. This is what will then deploy it. And then this will be the deployment summary for you. Just a few changes will be maybe, this is where, for my case, this is where it was deployed, is the address. So if I was to go on chain, I would look for this address and see my contract. Then this is the transaction hash, the gas used. So these are, even the compiler used, these are my summaries. So for you, again, to be a bit different, but it's the same thing. Then interacting with the deployed contract, I had already mentioned that you would add interact.s.sol inside the script, and I had already shown you that this is the command you paste there. You may also want to have your logs stored. If you want your logs stored on chain, you would create store interaction.s.sol and paste this. So all these I've explained in my previous class. And of course, I've shown you the difference between interact, hung verifier, and store interaction. These are just the differences of this. But when you run them, you get to see the differences clearly. That is the difference here. There are two modes. One is verify, read only. There's no gas that will be used. And this other one is verify, store, and store. So this one, there'll be transaction used, and it will store the state. So you can find your logs on chain. That's what it means. I've just tried to summarize the differences here. Now, what is our summary? What have we learned today? We build a ZK circuit that proves that given two integers x and y, whose products 42, and then we can reveal their sum. But the proof was just saying that he knows two values, x and y, whose product is 42, and gives the sum of those two values. It's a zero knowledge proof. The verifier does not get to know what these values x and y are. How to test and generate ZK proof using Noir and Buttonbug. We've seen that. And we have also seen how scroll operates on ZK EVM layer 2. And we've seen how to deploy and interact with the verifier contract on scroll. I've also seen the differences between off-chain and on-chain verification. In case of any questions, you can always reach. You can do an email, Twitter, and so on. If there are questions, would love responding to them. Thank you.